All right, here we are, Mr. McMurray again. We're gonna full of energy today because we're talking about chapter 6, and it has a lot to do with energy. All right, and we've talked about force a little bit. Force is equal to mass times acceleration. Okay, and we usually measure force in newtons. All right, and so the formula for, or the units, excuse me, the units for newtons are kilograms, which is what we measure mass in, times meters per second squared, which is meters per second per second. In other words, how acceleration, how many meters per second faster is an object going per second. So every second it's going how many meters per second faster. Okay, so that's acceleration and that's a force. Okay, now forces are important because forces allow us to do work. All right. Now, we think of work as somewhere we go, we get paid a lot of money to be there, and that's good. Hopefully, if you get paid lots of money, that's even better, but you know, whatever. In physics, work is a little bit different. Right? Work is, formula here, equal to force times distance, or if we just put it in letters, W equals S times D. Okay, so work is equal to force times distance. So there's basically then two things that affect the amount of work that something done is. One, there must be a force exerted, okay, and to exert a force you need energy. All right, let's talk about energy just for a second. Energy is in chemistry, energy is the ability to cause change. All right. But in physics, usually we think about energy is the ability to do work. Okay. And so energy is what allows us to apply force. It takes energy to apply a force to do work. Okay. And work involves a force acting on an object for a particular distance. Okay, how far does it work on it? So the two things have to happen. A force has to be applied and an object has to move a certain distance. So in order for there to be work done, you have to have a force, or in this case, the guy has to pull on the pulley enough to lift the bag here full of concrete or whatever. And the force required would be equal to the weight of the bag, basically, because he's lifting it up against gravity. So he would have to put enough force to equal to the weight of the bag. And he would pull it a certain distance. All right, so from this first floor up to the second floor, and that would be the distance from here to here, and the force would be the weight of the bag. And so you would do newtons times meters. Now, the units then can be called Newton meters because you're doing newtons times meters, so sometimes they're called Newton meters, or named in honor of a scientist who did a lot of physics work, joules, okay, or just a capital J for short. Okay, we won't be doing a lot of formulas, but when we do, you'll need to remember that units for work are either going to be Newton meters or joules. Now, if we pick this bag up from the floor, the ground floor, all the way up to the second floor, how much work would that be compared to going to the first floor to the second floor? Well, the force would still be the same. We're still lifting the weight of the bag, but the distance would be from here all the way up to the top, so that would be twice as much work being done. Why? Because we went twice the distance. All right. On the other hand, if we lifted two bags from the floor up to the top, that would be double the amount of work it would take to take one bag, or four times if you took one bag up to one floor. Okay, because now we have twice as much weight and we're going twice as far. We're going 2 stories, so you would end up with 4 times as much work. So the amount of work we do depends on how much force, in this case the weight of the object we're lifting, and how far are we going to carry it. Now there's one other caveat or rule that goes with that, and that is that in order for work to be done, the object has to move in the direction of the force being applied. So now let me explain a couple things real quick. If we go up here and we look at this guy, all right, if I'm pushing against a wall, or this guy's pushing against the wall, all right, is there any work being done? Well, is he applying a force against the wall? Yes, he is. Is the wall moving a distance in the direction of the force? No, it's just sitting there. Okay, so technically there's not being any work being done. Now, someone says, but will he get tired if he's pushing against the wall? Yes, he most certainly will. He is exerting an effort. He is putting a force on the wall. He will eventually get tired if he continues to do that. But technically, physics-wise, no work has been done because the object is not moving. So the object must move, and it must move in the direction of the force. All right. Now, if we bring the weightlifter, all right, if he lifts this weight up to here, then has he done work? Yes, because he's lifted the weight, a force equal to the weight of this, however many newtons this weighs. All right, he's lifted that, and he's moved a distance from the floor up until here. All right. Now, if he holds that weight right there, is he doing any work? And the answer is no, because it's not moving a distance. Okay, even though, yes, he will get tired of holding it here. He's having to hold it to get here. He's exerting a force to keep the weight up off the ground. All right. If he carries it very long, he will get very tired. But since it's not moving a distance, then there is no work being done. Now, if this guy were to start walking around carrying the weight, would there be work being done? Yes and no. His arms are still not doing work on the weight, okay? Because his arms are exerting a force up to hold the weight up, whereas gravity is pushing it equally hard down, okay? But the weight is not moving in the direction of the force from his arms. Only if he starts lifting the weight up, which is the direction of the force that the arms are exerting on it, only if the weight starts moving up will he do any work. Now, he's walking around, so his feet are applying a force to the ground, and it is moving his body and the weight in the direction of the force. So you could argue that his feet are doing work, okay? But his arms, even though they're getting tired holding this stupid weight up, are not doing work because the weights are not moving in the direction of the force that is being applied. All right, now let's look at another example, having to do some work. Boom, here we have a ramp and we have blocks of ice. We'll assume that they are completely equal. All right, and we have two different people. We have the girl pushing the ice up the ramp and the guy is lifting it up at the end. Okay, and the first question we would want to know, who is doing more work? Okay, the girl pushing up the ramp or the guy lifting it up here? Okay, and ultimately they are both doing the same amount of work, okay, and lifting the block. Okay, so basically both of them are getting the block from down here at ground level up to the top of the ramp. Okay, now the guy is pushing this block of ice. He picked it up, so the force it would require would be the weight of the block. Okay, so he's however many newtons that block of ice weighs, let's just say it's 50 newtons. He's picking that block up from the ground up to here, so he's using that much force, and his distance would be from here to here. So you do force times distance, and that would give you however many joules. Okay, but the girl is pushing it up the ramp. Now, does it take more force to pick up the block or to push it up the ramp? And the correct answer is it takes less force. So she's using a lot less force. That's why we tend to push things rather than lift them if they're very heavy, like furniture and things like this. It's a lot easier just to push them than it is to lift them up because it takes less force. So it says, so she's going to do less work because she's not using as much force. But in fact, she's going to use the same amount of work because she, instead of just lifting at this distance from here to here, the height of the ramp, she is pushing it the whole length of the ramp. And so her distance is going to be high. And so even though the amount of force she has to use is less, the distance that she has to push it has increased. And so she will be doing the same work as the guy who lifted it up because he has to use more force, but he only has to do it a shorter distance. And so they kind of cancel each other out. And basically the bottom line is there is no shortcuts. To lift the block from here up to this height, whether you do it manually, directly like the guy did, or whether you push up the ramp like the girl is, it's still the same amount of work. We want to do a certain amount of work is going to take energy, because we said energy is the ability to do work. And if we want to know if we have enough energy to do the work, we figure out how much joules of work needs to be done, or Newton meters, to lift it up here, and then we can calculate how much energy is going to be required. Energy is also going to be measured in joules, which makes sense. Since we use energy to do work, and it's the ability to do work, it's going to be measured in the same units that we measure work in. So energy is also going to be measured in joules. So if we know how much work something requires in joules, then we can figure out how much energy it would take to do that. Now, another thing besides work, but similar but not the same, is power. You hear a lot of times on pickup trucks and stuff, and they're talking about power. Okay, and they'll talk about how much the truck can lift and carry and pull and all these sort of things. But in physics, power has a very specific definition, and basically, power is equal to work divided by time. Okay, and so if we do that, the units that we would use are called watts. Basically, you've got kilograms times meters squared divided by over seconds squared divided by seconds, and you end up with this unit. But basically, the good news is you don't have to worry about this. You just need to know that power is measured in watts. Okay, and what power then is how fast can you do the work. Okay, for example, we said both the girl here and the guy picked up the ice and did the same amount of work. But if the guy lifting it up did it faster and took less time, okay, a smaller amount of time, then there's going to be a bigger amount of power. Okay, the denominator is small, that makes the fraction big. Now, if she pushed it up the ramp, if it took more time, therefore this was bigger in the denominator, that's going to make the power less. She has less power. Okay, so power is about how quickly you can do it. So technically, if a commercial wanted to say one truck is more powerful than another, what it would want to do is show not only how much could they lift, give two pickups equal loads, but to see which one could pull it to a certain distance faster. Okay, and so that would be measuring power. So when we say a Chevy or Ford or whatever has more power, it would have to do with how quickly it can do it. So basically it's work divided by time, or force times distance divided by time, because that's basically what work is. All right, and so the more work you do, the less time you do it in. And it was named after James Watt, who invented the steam engine, which was one of the big breakthroughs and allowed machines to be much more powerful and help power the Industrial Revolution. And so it would do a lot of work in a short amount of time, so it's kind of fitting that it was named after James Watt. All right, that does it for power. I'll come back and we'll talk some more about energy and types of energy.